Okay, so we'll continue with the our study of the Lorenz system, and what we are going to do is let me once again draw the bifurcation diagram as a function of the parameter r, essentially this figure again. So I have that's my origin, and the origin is a stable fixed point till r equals to 1, whereby it loses its stability through a pitchfork bifurcation, and I have two stable fixed points emerge over here, which in turn lose their stability at r equals to RH, and I have these unstable limit cycles, and beyond this point, so this was the point where the let me draw. So these are the unstable limit cycles. So how does the fixed point, let's say this one, looks like? So this is, remember, it's 3 dimensions. So in 3 dimensions I have the fixed point C plus, let's say this is stable, and not only that, it's surrounded by this unstable limit cycle and it spirals in over here. So this is the unstable limit cycle. I should have drawn it dotted, doesn't matter. Unstable limit cycle. Now as the parameter increases to RH, this unstable limit cycle shrinks and collides with this point, makes this point unstable, and then there's a question mark. There is no stable attractor anywhere, and we'll come to know that the trajectory immediately jumps on the strange attractor or the fractal. Uh, so for R greater than RH, trajectories fly away to a distant attractor. We don't still know what that attractor is, but that's the whole idea. And this is a partial bifurcation diagram of the scheme that's happening. And that essentially is what's happening. So this is a kind of an unstable limit cycle which actually is occurring in, I can also call it a saddle cycle. This is a new type of unstable limit cycle that's possible only in phase spaces of 3 or more dimensions. So this cycle has a 2-dimensional unstable manifold, this one in this plane, and it also has a 1-dimensional stable manifold. Okay, so of course, since this is unstable, any trajectories outside also go away from this limit cycle. The focus of this chapter is going to be what happens beyond RH. So Lorenz explored this numerically. So let me say chaos on a strange attractor. So Lorenz studied these trajectories numerically, and the parameters he chose was sigma 10, b equals to 8 by 3, and r equals to 28. So notice the value of RH, this guy, uh, is, so let me just copy this. So RH is plugging in these parameters. Uh, RH came out to be for the above parameters 24.74. So Lorenz is beyond RH. So Lorenz is doing this numerical simulation somewhere here at 24 point. So RH is 24.74, and Lorenz is somewhere here at 28. His numerical calculations, and for these set of parameters, he noticed very strange erratic behavior. Uh, so after, so if you plot y as a function of time, he noticed some so you can see that after this transient, the trajectory settles onto a some sort of an aperiodic oscillations, and once he plotted it on the phase space, let's say this was x, this was z, he saw again similar kind of this beautiful patterns, some sort of a, actually I should be drawing it. I don't know how to even draw this, but you get the idea. There are enough, and then it again goes to this wheel. Of course, these trajectories are in a third dimension also, so they look like they are intersecting each other. They are not. And then again, it goes to one of these guys, goes again, goes again. So these are the two wings of the butterfly. and you get these beautiful patterns which you see. Uh, so even though the trajectories appear to cross each other, this is just an artifact of projecting something in the 3 dimensions onto a 2-dimensional plane. So the trajectory starts at the origin, then goes to one of these things, revolves, then goes to the other thing, makes revolutions. These are the 2 fixed points. Again goes over here. The amount of circles it's taking in one of these wings or this wing, this is random. Random revolutions on each of these wings, and just twists and turns randomly circling this one, randomly circling this one to make these wings of a butterfly. And uh, when you visualize this trajectory in 3 dimensions rather than 2 dimensions, it appears to settle on a thin set. In 3D, it settles on a rather thin set. Looks like a pair of butterfly wings. Just a minute.